Good morning and welcome to this new Seagal video. Today we are delighted to have for this webinar Pat Connolly, who is going to discuss theoretical versus actual Chi. Next slide. Pat, next slide.
I've done it. It should show up.
So first of all, thank you for signing up. So we plan to run this session over the next 4 weeks, so please sign up. Tell us what you want to see. We can add more videos after this session ends, so let us know. If you want to find out more, please contact your Seagal account manager or email at sales@seagal.com. Next. So the format, each session will last between 20 and 30 minutes. Each session will be recorded and you will get a copy of the recording via email 24 hours after the webinar ends. The recording will also be loaded on the Seagal YouTube channel if you want to see it again. If there is time for question, please submit your question via the chat tab in the GoToWebinar console and Pat Connolly will answer your questions. So I think this is the end for me. So I hand over to Pat. Thank you very much, Pat.
Okay, and good morning, everybody. So let me just start off with a few contextual points. I'm going to assert that the purpose of AVO is to make better seismic data sets. Better data sets can simplify qualitative or quantitative interpretation problems. New data sets are created by combining intercept and gradient volumes using this equation, A cos chi plus B sin chi. So this talk is about finding the best chi angles. There's clearly a bit of delay on the refreshing of slides, so I'll try and pause slightly between each one. First thing to point out is that we have theory to relate chi-angle projections to elastic property reflectivities. So what that means is if there's a change of an elastic property, any of these listed here, across an interface, that will cause a change in the intercept and the gradient value, and that will show up as a direction, a specific direction on an intercept gradient cross plot, something like this on the right hand side. What you can see is that the elastic property reflectivities tend to cluster in a couple of groups. So the things like Lamé parameter lambda and K bulk modulus sit around, somewhere between 10 and 20 degrees. And down at around about minus 45 degrees, we have things like, some very sheary things, shear modulus, shear impedance, Young's modulus. So things which, are going to be insensitive to fluid, but potentially sensitive to changes of lithology. And then up at about plus 45 degrees, we have VPVS and density. Important point to note, though, is that across an interface, it's pretty unlikely that only one of those elastic properties is going to be changing. So if lambda rho is changing, then mu rho is probably going to be changing as well. And the combined effect of the intercept and gradient across an interface is going to be the combination of multiple vectors. So you have to consider, multiple changes to figure out exactly what's going on, which kind of makes the situation a bit more complicated. I'm not going to go into any more detail on this now. If you want more information, I'll refer you to my leading edge article from last year. So theory will only take you so far because you need to know something about your local geology, and therefore you need to analyze local well data to determine what's actually going on. So we tend to estimate optimal chi angles initially from well data, and there are a number of different ways of doing this. Usual starting point is from an AIGI cross plot. I'll talk more about that in a minute. People also correlate extended elastic impedance curves with target logs with reservoir property curves such as V shell or SW, and get correlation curves looking like this, where they can pick out the optimum correlation. And another good thing to do is to just look at the details on a whole range of EEI curves for different chi angles. And this really is always an important point to finish on, I think, because a lot of the detail can quite often get lost in cross plots and correlation plots as well. So AIGI cross plots, these can be used to find the optimal chi-angles such that they maximize or minimize contrast between faces. So the plot here shows an AIGI cross plot from the North Sea, three main facies groupings, clean sands, which are mostly oil, shales and cemented sands. And if we just focus on the clean oil sands and the shale, using the scale software, we can determine an angle which will optimally separate out those two faces. So that's one approach, maximizing the separation between faces. But we can see in this case, we've also got some cemented sands in the mix. And this angle will be fairly close to an angle which will minimize the separation between the shales and the cemented sands, such that the cemented sands will drop into the background, which may be important. But that angle may be slightly different. So there are often sort of, conflicting ideal angles, depending on exactly what it is you're trying to do. This slide shows the more general case where we have shale, brine sand, and oil sand. The fluid angle, in principle, is defined as the line between the brine sand and the oil sand, so the direction of fluid substitution. But we've also got shales in there. So quite often we may just try to maximize the separation between the oil and the brine along that angle. But in some situations, it may be better and more advantageous to minimize the separation between the shale and the brine sand. In this case, that's going to be at a fairly similar angle, but it may be a little bit out. It's hard to tell in advance exactly which of those two angles is going to be best. Another important point to emphasize is just how variable the oil brine fluid angle actually is. It can really sit anywhere between about 0 degrees and 45 degrees. It actually depends on the relative change of bulk modulus and density. And that's going to depend on the rock mineralogy and the fluid properties and things like that. So it's often hard to predict in advance exactly what the fluid angle is. In general, it won't lie along one of the lines of pure elastic property reflectivity. So it won't lie along the lambda rho or the lambda or the K rho, any of those. It could lie somewhere else. The other angle of importance usually is the lithology angle. So this is the angle orthogonal to the fluid angle, such that the brine sands and the oil sands have the same impedance. So we're minimizing contrast between the brine and the oil. Now this projection is only going to be useful if the shale points are offset from this line. Now in this case, I've shown the shale points in a pretty favorable position, offset from the sand line, such that the lithology projection would highlight the positions of the sands irrespective of the fluids. But that won't always be the case. Sometimes the shales will sit in a particularly unfriendly position, as shown here. And in this case, the lithology projection probably won't be very helpful and won't show up very much. And that's not an uncommon situation. So one of the early parts of analysis, AVO analysis, is to determine, are you in an AVO friendly position or not? Are all your faces on one line, or are they separated out in two dimensions? This will show up when we're doing correlations with reservoir property curves as well. So this shows a modeled AIGI cross plot. This one is an AVO friendly one with the shales offset from the sands. And in this case, if you do correlations with VShale and SW, you'll get fairly clear indications of the maximum or minimum correlation as shown here. But if you happen to have a fairly unfriendly data set with the shales now shifted so they're in line with the sands, your correlation plots will look something like this. Very little discrimination depending on the chi-angle. So essentially AVO is not working for you in this situation, and it's not going to be very advantageous to come up with multiple volumes. And you'll see this, you should see this straight away from the correlation plot. So let's think about seismic data now. So here's a modeled AVO curve, just using the standard AVO equation shown down there at the bottom. And with seismic data, we usually assume that there's going to be some error with the data. So I've indicated that by putting error bars on each of the data points. Now, if I just added random noise to all those data points, something like this diagram on the right, I could still fit a regression curve through those data points. Something like that is an animation of a regression curve going in. Hopefully you can see that. And if it was only random noise, we'd get a pretty good estimate of the intercept, the gradient, and the curvature term. But sadly, that's not really what the situation is with seismic data. Now, measurement errors have got two components. They've got a random noise component, which just causes a spread in the individual values, but they've also got a bias. which is an offset of the mean value from the true value. And us geophysicists seem to be rather poor at discriminating between these two situations. We often assume it's just random noise, where in actual fact, most problems we deal with are caused by bias, and that's a much more difficult problem to deal with. So for example, if we have to estimate incidence angles, all the AVO equations are parameterized with incidence angle, and those have to be estimated by ray tracing through the overburden. And that means that the error in the estimated angle is going to be proportional to the error in the local interval velocity just above the interface. And you know, if you're just relying on seismic interval velocities, they're never going to be accurate enough to get accurate angles. There's always going to be some error in the interval velocities, just due to a lack of resolution, if nothing else. So what this will do, though, will be introduce a bias on all the data points on a given AVO curve. If the local interval velocity is wrong, then all the angles estimated for that interface or that location will all be shifted one way or the other. So this, this illustrates a curve with a 5% angle error, all shifted one way. And in particular, that's going to have a significant impact on the curvature estimate, but also the gradient as well. Typically, what this means is we can't estimate the curvature term, which is why we tend to always fall back on a two-term AVO equation. This diagram just shows how big the curvature term error is in the presence of angle estimation errors. So the horizontal gray line is the true curvature value, and the blue line is the estimated curvature value. And you can see if we're only 10% out with our angles, in other words, if we had a 10% error with our interval velocities, we could be double or half the true value. So curvature term estimate is unstable, and that's why we always tend to fall back just to a two-term approximation, intercept and gradient, using the so-called Shuey equation shown here. But that introduces its own problems, because now we have to exclude the curvature term when we're estimating the gradient. So this diagram here again shows a modeled AVO curve, and it's turning up at the end with the curvature term. Then the black line is my estimated gradient, and the orangey line is the true gradient. And in this case, I've only muted out to about 50 degrees, which is nowhere near enough. And that means, of course, that the gradient is biased because of the curvature component. If I reduce the maximum angle, the bias will be reduced. But to reduce it to zero, I really have to reduce the angle or the maximum angle to a very low number indeed. And as the maximum angle gets smaller and smaller, that means we're measuring the gradient across less and less data and become increasingly sensitive to the random noise in the data, and the gradient will start becoming quite inaccurate. So this is summarized on the next point, the next slide. What I have here are the statistics from 200 gradient fits to noisy data. And for this first one, I've muted the data at 30 degrees, which is the usual guideline for maximum angle to avoid the curvature term. The vertical dashed line is the true gradient value. And what you can see from the measurements is that we still have bias, fairly significant bias. The average value is offset from the true value, and we've got a fair bit of spread on the measurements coming from the random noise. So I can reduce the bias by reducing the maximum angle. So if I go down to 20 degrees, you can see here that we've now, the offset of the mean value is now less bias, but at the cost of increasing the spread. So this data would look noisy. If we go the other way, up to 40 degrees, we can decrease the noise, but the cost now is that we're increasing the bias. So the usual guideline here is that it's better to be vaguely right than exactly wrong, which means we should generally err on the side of less bias and more noise, which is not our general instinct. We tend to go the other way by instinct. But in summary, the maximum angle, it now becomes a critical parameter. This really requires some fine tuning as to what maximum angle you go out to. And that means you need a lot of angle stacks. Having 3 or 4 angle stacks is not enough. You need a lot more to allow you to fine tune the maximum angle. And whatever you do, you're probably still going to finish up with amplitude errors round about plus or minus 10%. And if we look at the kind of list of other sources of measurement error, most of them are going to cause bias on the local AVO event. So inaccurate angles we've looked at, non-flat gathers will cause bias, incorrect offset scaling will cause bias, and so on all the way down. All of these will cause bias. Now the bias may be just local. It may be just local to that particular event at that location, or it may be global. If your offset scaling is incorrect, that's going to cause a global bias probably across your entire data set. But it's still bias at the scale of the individual event. So let's have a look at a few more of those. Variable offset tuning. Events tend to generally move closer together with increasing offset or increasing angle. So I've measured or I've modeled these two events just using a smooth compaction velocity. And the separation at 0 angle is 20 milliseconds, and at 30 degrees, it's 18 milliseconds. Now, events that close together will be subject to tuning, but the problem now is that the tuning at near offsets will be different from the tuning at far offsets. So we can work out how much different. And the diagram now on the left shows how different the tuning is. So it's a difference between 2 points from the right-hand curve. So if the two events are far apart, there won't be any tuning, it won't be a problem. But as the event gets thinner and thinner, the relative change of tuning, the differential tuning, will increase. And again, it's kind of varying round about plus or minus 10%. So we're probably introducing more plus or minus 10% errors because of tuning. Scaling errors, I already mentioned. It's extremely difficult to get your offset scaling exactly right, because there's no real way of knowing when it is exactly right. You can't look at a gather and know that it's correct. The image I've taken from Rob Sim and Mike Bacon's book, Seismic Amplitude. They scale this gather 2 different ways. They look virtually identical. But if you measure the event in the middle, that strong event, the gradient is actually different on those two. And again, it kind of looks like about a 10% difference. And if you can't even see the difference looking at the gather, it's highly likely you're going to have 10% errors again, or a minimum 10% errors in your gradient estimates because your offset scaling isn't precisely correct. So all this means that it's effectively if you think about the effect of this on an AIGI crossplot, essentially what this is doing is moving your data points primarily up and down on an AIGI crossplot. There may be some error also on the AI component, but it's mostly the GI component, which is essentially moving up and down because of the measurement errors from your seismic data. And that means that the chi angles are going to change. The chi angles are the angles between these different faces, and depending on the source of your error, these chi angles are going to change. And the nature of the change is, is going to be fairly subtle. It's going to depend on the nature of the error. It's going to depend to some extent on the AVO class of the data, all sorts of things. So different errors cause points to move in different ways. But the net effect is still going to be that your chi angles from your seismic data are going to be different from the chi angles you'd estimate from well data. Another consideration is anisotropy. We know the subsurface in general is anisotropic, particularly shales. From Rubin's equation, we know that VTI gradient is equal to isotropic gradient plus half the change of little delta, the Thompson parameter little delta. If we translate that into gradient impedance, it means that our VTI gradient impedance is equal to isotropic gradient impedance multiplied by the exponential of little delta. Because we make AIGI crossplots with logarithmic axes to get the angles correct, essentially what that means is that if we were wanting to include an anisotropy term with our shales, all we have to do is just add the value of little delta to the gradient impedance value of all the shales, which typically will just shift everything up a bit. So here I've modeled it with a little delta of 0.07. And in general, we might expect shales to have a value of, typically around about 0.1, could be more, could be less. And that's probably a better guess than assuming it's all 0. So, good practice is probably just to add 0.1 to all your shale points, assuming that's a better guess than 0. The overall effect of this is going to be that the actual chi angle, the chi angle you're going to finish up with from your data, will be different from the apparent chi angle. The apparent chi angle is the one you've coded the data up to provide. And this shows a cross plot of apparent chi against actual chi for a fixed angle error of 10%, which is probably pretty typical, and a range of scaling errors going from plus or minus 15%. And what you can see is if we're working with relatively small angles, up to about 30 degrees, and the errors are pretty small, but they grow quite large as we get much above that. So when you're getting above, say, something above 45 degrees, the errors can get pretty big. So you may code up, for example, to get a chi-angle of 60 degrees, but you may finish up with an angle anywhere between 45 and 90. So what that means is that you can't rely on your coded chi-angle to actually provide what you think you're actually getting from the seismic data. The other thing we have to worry about is the effect of random noise. Random noise still has an effect, and it's the well-known noise ellipse on an intercept gradient crossplot. So here I'm modeling random noise only. I'm measuring the intercept and gradient through a whole lot of random noise, and what tends to happen is the regression line just pivots mostly through the center of gravity of all those points. That causes an inverse correlation between intercept and gradient, and that shows up as a very steep ellipse on an intercept gradient crossplot. So the effect of that is going to be that when we create a chi projection aligned with the minor axis of that ellipse, which will typically be round about 7 degrees, which is the angle of a conventional stack, then we'll have minimum noise, as shown on the diagram on the right. And when we have a projection aligned with the major axis of the ellipse, which will be orthogonal to that, about 97 degrees, that's where we'll have maximum noise. So in general, the gradient is typically the round about the maximum noise. Now, how much the noise increases will depend on the quality of our data. If we have really high quality data, it's been well processed and well conditioned, then the increase in noise level may not be all that bad. But if we have poor quality data, then the noise level can increase quite dramatically, meaning that quite often high angle projections are essentially unusable, and we're restricted to a low range of angles. In any eventuality, it's quite likely that that will be pushed down towards a lower angle than the theory might suggest, because the signal to noise will be higher at lower angles. So noise levels increase from the stack angle up to the ortho stack. So summary so far. Gradient measurements will always be inaccurate. There'll be lots of plus or minus 10% errors, and some of these it's virtually impossible to eliminate. We can do our best with the processing and the conditioning. We can make sure our gathers are flat and multiples removed and so on. But it's extremely difficult to have accurate angle estimates everywhere, or ensure our gathers are scaled correctly everywhere, or to compensate for anisotropy everywhere. So we're going to have errors coming through whatever, and we have to make an allowance for that. Anisotropy contrast will change the gradient. And also the definition of what an optimal chi-angle actually is not always clear anyway. As I mentioned earlier on, sometimes we're trying to minimize contrast between faces, and sometimes we're trying to maximize contrast between faces. And which one is best, is very much data dependent. Noise will increase for higher chi-angles. That always tends us to push us towards lower angles. And the end result of this is that selecting a chi-angle is a highly subjective process. It is not some process which results from just a theoretical analysis, or even just a straightforward empirical analysis of the well data. It's a highly subjective analysis which depends on you looking at the seismic data. So most definitely you should not use theoretical or well-derived chi-angles and just apply those blindly to the seismic data. What that means is that we have to inspect the seismic data. So here's my favorite data set for illustrating this from offshore Angola, showing a fluid projection at the top and a lithology projection below. So we've got the reservoir dipping down here, oil water contact through there. So the fluid projection shows the contact highlighted very clearly, and on the map in particular, whereas the lithology projection shows the brine sands to the full channel from the oil leg down to the brine leg. And in practice, what we would do is just scan through a range of chi-angles to pick out the best images. Now, unfortunately, I don't have the original projections or chi scan that we used to do this some time ago now. So I've simulated this in PowerPoint, but I think you'll get the idea. We'd pick out the data set which gave us the sharpest cutoff of the fluid image, and the one which essentially closed down the effect of the change of pore fluid to give us the overall best image through the turbidite channel. And if your data looks like this, then that would be a pretty easy process to do and to pick out. Many times your data is, is not as friendly as this, and it's a much more subtle process. So of course, Seagal provides some useful software to help you with this. So this is illustrating their kite scanning software. Now I'll set this going. Unfortunately, this is not the most entertaining data set. It's a very small postage stamp through a North Sea field, and there's not enough data to really provide any geological context for you to see exactly what's going on. But hopefully it's enough for you to get the idea. What you should be seeing is the sectional view and a map view scanning through a full range of angles, and that would allow you, if you could see more data, to pick out the two angles in particular, a fluid angle and a lithology angle. But you'd be very much informed by the empirical information from the well data. You'd sense check the angles from the theory, but ultimately you're going to fine tune the angles by selecting them from your seismic data and essentially using your judgment to pick out what you think looks best, because that really is, you're the ultimate arbiter in this. So I'll wrap up there. Just summarize with these points. Well data analysis supported by theory provides candidate optimal chi-angles. Often the objective is to simplify interpretation problems by minimizing contrast between facies. Gradient measurement errors cause actual seismic chi-angles to differ from apparent chi-angles. Chi-angles from well data or theory should not be blindly applied to seismic data. Seismic data must be scanned through a range of chi-angles and the best selected by eye. Okay, that's it. So thanks for your attention, and I'll pick up and try and answer any questions that you might have now.
Thank you very much, Pat. So yeah, we have some questions. So yeah, thank you for watching. We love your feedback, so let us know what you want to see. If you have any question that we can't answer, please do not hesitate to ask through the support email, support.geo@seagal.com. And don't forget to register for the next video where we were going to talk about how to model your velocities with blueback rock velocity. But we have some questions for Pat. So the first question is lithofluid cube concept useful? Seems a confusing mixture, or is it like maximizing shale versus non-shale?
Sorry, can you repeat the question? It was the fluid. I didn't quite
The
pick up again.
lithology and the fluid cube concept, is this useful?
Yeah.
It seems to be a little bit confusing, or is it maximizing the shale and the non-shale?
Right.
Behavior?
Okay. Right. So yeah. So I think I think these are a kind of flexible concepts. I was trying to get across. I mean, certainly they are useful. I mean, in general, what we're trying to do, I think what we're trying to do is to simplify problems by thinking about minimizing the contrast between pairs of faces. Mostly, you'll have multiple faces on your data set. And if you just take a conventional stack as it comes, there's a mix of faces, and it can be quite hard to understand what's going on. You can use AVO to simplify the problem by minimizing contrast between faces. So, as I said, a fluid projection can be something which you can think of as minimizing the contrast between, say, a brine sand and a shale, to leave the oil sands separated out, which will give a clearer image. Or you can think of a lithology projection as something which minimizes the separation between the oil and the brine, leaves all the sands looking the same, and maximizes the contrast between the shales and the sands. And the combination of those two, the combination of a fluid and lithology projection, I think are extremely useful if it works. Usually, if you've got high porosity sands, then you'll be able to get some form of fluid projection out. But whether you can get a lithology projection depends very much on the relative position of the sands and the shales. And that comes down to just, things around the mineralogy of the shales in the basin you're working in and things like that. It's hard to predict in advance. You just have to analyze your data and just see how it looks. Do they separate out in 2D on a cross plot, or do they not?
Okay, thank you very much. We have other questions. So in our tool, Seagal Seismic Reservoir Characterization, for the creation of intercept and gradient, we have several methods for estimating the gradient. Do you have any suggestion or recommendation to choose between them?
Yeah, it's a very good question. I mean, I think, so, we know that full AVO curve, has got, is at least a 3-term curve. running up to the critical angle, so least intercept gradient and curvature. And you can do a 3-term estimate. And I demonstrated that you can do a 3-term regression fit to estimate intercept gradient and curvature. But my feeling is that because of all the bias in the amplitude and the angle estimates, the impact of that on the curvature is so severe that trying to do a 3-term fit usually results in a worse fit. Even if you sort of do a 3-term fit and throw away the 3rd term and just use it to get a better estimate of the gradient, that too seems to be often unstable. And we've done, Lisa's done some trials. We have done trials testing that, and generally the 3-term fit results in something which we generally don't like very much. Now, I don't want to be, too prescriptive here. It may be that if you really fine-tune the maximum angle, and include a small component of the curvature, maybe you can get a better result. But it's a little bit, it is a little bit error-prone, without doubt. So I think your starting point and the general default should always be a very simple, straightforward 2-term fit as your starting point. And then maybe experiment with some of the other ones, but with a high degree of caution, I would say, if you're going to try anything else other than that. Lisa, I don't know, do you have any comments on that as well, from your experience?
No, I always use a 2-term because I prefer it. So we have another question. I think it's a good one. So carbonates, how good the Chi angle prediction for carbonates? I think a lot of people would like to apply Chi projection or carbonates. Do you have any experience or any comments on that?
Limited experience, but my general impression is that AVO is generally not much use for carbonates. Okay. Usually what you get, there's a wide range of carbonates, I know. Lisa is the expert on carbonates, and I'm sure could say more, but in general, for a conventional, reefal carbonates, you just don't get any useful AVO effect. All you've got is booming strong amplitudes right across the gather, across all offsets. And usually that means you're falling back on a straight stack, a conventional stack. And it's rare, I think, that you could do anything much more than that. I wouldn't discount it. It's always worth checking. It doesn't take long just to check to see if you can see anything more. But I must admit, I can't think of any examples off the top of my head when AVO has provided very much value for carbonate analysis.
Okay, thank you. So one last question. You showed us how to use AVO for lithology and fluid. How to use AVO for porosity estimation?
Right. Okay, that's a very good question. I think I put this in the context of using Odyssey, or Seagal's probabilistic inversion. I think where we are on that is that if you've got a reservoir, well, I think in general, we're focusing these days very much on phases probabilities as being the primary output inversion. The purpose of modern inversions, I think, is to estimate phases probabilities. And therefore, what you would need to do is to set up, rather than trying to estimate a continuous porosity curve, which I think is somewhat ambitious, probably what you should try and do is to separate your reservoir into multiple phases of variable porosity. And if you've got AVO data, really you can only separate out 3 phases anyway. From 2 volumes, you can get 3 phases. If you've got a variable net to growth reservoir, that essentially means you might have shale, high porosity, and low porosity sand. And that would be it. So you'd be trying to separate out 3 phases. To do that, you would need to come up with chi angles, one angle each to separate out or close down the separation between pairs of phases. So you would have one projection which would make the 2 sand faces look the same, and you would have another projection which would make the shale and one of the sand faces look the same. So you would reduce it from a 3 faces problem to a pair of 2 faces problems, which you can then solve. So in that situation, you could then solve for the proportion of the high and the low porosity faces, and then the proportion of those 2 would give you an estimate of the average porosity through the reservoir. I think that's the best approach. So I'll leave it there. Probably people to say on that, but I'll leave that there.
So it's perfect. So I think we've use all our time. Thank you very much, Pat. Thank you very much, everybody who watched. And do not hesitate to ask your question again, so either to the webinar email or to the support.geo@seagal.com. Thank you very much, and I hope to see you next week. Bye-bye.